Here we'll show our flood monitor application and demonstrate our beacon movement classification AI model. We have developed a mobile application, Flood Monitor, to provide the data and analysis from our system to the end users in an informative and easy-to-use manner. In this demo, we'll consider a theoretical scenario of our system being used to monitor a flood north of Bangkok. The application consists of 3 tabs which can be accessed using the navigation menu at the bottom of the app. The first tab, My Status, shows us whether or not we are inside an active early warning system ellipse and the most relevant information from the EWS message for that ellipse. For the moment, we are safe outside the ellipse, so let's take a look at the second tab, Prediction Map. We are currently viewing the EWS area on the map, and as you can see, we are just outside the area, so our status is safe. Now let's see what happens if we enter the EWS area. Notice that now we are inside the EWS area, a notification has appeared in our phone status bar. It reads, Flood Monitor EWS Alert, and informs us that we are inside an EWS area. If we try to close the notification, it will return as we are still in danger. It will even appear if we have the app running in the background. Now let's go back to My Status to see what information it provides about the EWS area. As you can see, the most relevant information from the EWS message is provided here, such as the event severity and duration. Now let's go back to the prediction map to see the data gathered by our service that could guide the creation of this EWS area. Our system consists of 2 types of beacons, static and dynamic, that are used to monitor flood progression and make predictions about flooding. Static beacons measure flood depth at a fixed location, and dynamic beacons are released into the water to track flood velocity. Here you see the static beacons mapped with their predictions of flooding in the surrounding area. These predictions are made by comparing the measured flood level at the beacons with the elevation data of the surrounding area. For example, here we see that a flood level of 2 meters has been extrapolated to the surrounding area within a 5-kilometer radius of the beacon. Now let's look at the data from the dynamic beacons. In this example, we have 5 dynamic beacons which have been released earlier from the same location as some of the static beacons. As you can see by the blue trails, they have followed the floodwaters south and have diverged from the rivers mostly into the central farmlands. The arrows show the current average direction of the beacons, while the areas in front of the beacons are based on a 95% confidence interval for their location in the next 2 hours, generated using a Gaussian process regression model. If we click on one of the beacon arrows, we can see information on the beacon position, the predicted flood speed, and the classification by our AI model of whether or not the beacon is moving in a circular path. We can also click on Overlay All Areas to see the EWS area overlaid with the data from the static and dynamic beacons to have a complete picture of the flooding. In this example, we can see that the flooding is concentrated around the river and the farmland to the west, with the floodwaters mostly moving south towards Bangkok and the sea. Now let's see what happens when we leave the EWS area. Notice that we receive a new notification telling us that we are out of the area of danger. We are now able to dismiss both notifications. Now we will look at the water quality map. Here we can select any one of the beacons and view the latest water quality data gathered by its sensors. The readings for the beacon can be seen in the tooltip and in the text view at the top of the application screen.
We are going to show now a demonstration of our artificial intelligence model behavior using an example of non-circular and circular dynamic beacon movement classification. For this test, we have reproduced both types of movement with our presence. In the video, you can now see a non-circular example. The position of this presence is being recorded and processed to generate a 24 by 24 black and white image that is classified by the AI model on the board in almost real time. The result for the black and white classification is non-circular with a probability of 100%. We have also input the color image to our color model, and the result is non-circular with a probability of 97%. The information of both the position and the AI model results are uploaded to our database to be read by the smartphone application. Now we are showing the demonstration of a circular movement. As before, the position of this presence is being recorded and processed. The black and white generated image is transformed from JPEG to PGM format to be received by this presence AI model. The result of the black and white classification is circular with a probability of 100%. The result of inputting the color image to the color model is circular with a probability of 99%. The accuracy of the model varies depending on the input data. In the case of movements that are not clearly circular, the AI probability output by the model decreases. Again, we upload the data gathered from the position and AI output to be processed in the Flood Monitor smartphone application.